Good morning students. Welcome to physics class. Today's video we are going to discuss about specific heat capacity of a gas. Also Meyer's relation. Specific heat capacity of a gas. This plays a very important role in determining the structure and molecular nature of the system. Specific heat capacity of a gas is used to determine the structure and molecular nature of the system. There are specifically two specific heat capacities. They are specific heat capacity at constant pressure Sp, specific heat capacity at constant volume Sp. What are they? Specific heat capacity at constant pressure Sp, specific heat capacity at constant volume Sv. Let's see one by one. The amount of heat energy required to raise the temperature of 1 kilogram of a substance by 1 Kelvin or 1 degree Celsius by keeping the pressure constant is called specific heat capacity of gas at constant pressure. Okay. So first one, specific heat capacity at constant pressure Sp. The amount of heat energy required to raise the temperature of 1 kilogram of a substance by 1 Kelvin or 1 degree Celsius by keeping the pressure constant is called specific heat capacity at constant pressure. Similarly, specific heat capacity at constant volume, that is same definition, but instead of pressure constant, here we are keeping the volume as constant. So the amount of heat energy required to raise the temperature of 1 kilogram of a substance by 1 Kelvin or 1 degree Celsius by keeping the volume constant is called specific heat capacity at constant volume. I repeat, the amount of heat energy required to raise the temperature of 1 kilogram of a substance by 1 Kelvin or 1 degree Celsius by keeping the volume constant is called specific heat capacity at constant volume. This is denoted by SV. Now let's discuss about molar specific heat capacities. That is denoted by Cp and Cv. Molar specific heat capacity. So there are two molar specific heat capacities, Cp and Cv. So what is Cv? The amount of heat energy required to raise the temperature of 1 mole of a substance. 1 mole of a substance by 1 Kelvin or 1 degree Celsius at constant volume is called a molar specific heat capacity at constant volume, Cv. Understand? The amount of heat energy required to raise the temperature of 1 mole of a substance by 1 Kelvin or 1 degree Celsius at constant volume is called a molar specific heat capacity at constant volume. Similarly, what is molar specific heat capacity at constant pressure, Cp? Same. If the pressure is kept constant, we can call this as a molar specific capacity. That means the amount of heat energy required to rise the temperature of 1 mole of a substance by 1 Kelvin or 1 degree Celsius at constant pressure is called molar specific capacity at constant pressure, Cp. Now let's see the relationship, that is what is the expression for Cv. Suppose if Q is the heat supplied to the system, supplied to the 1 mole of a gas at constant volume. So Q be the heat supplied to the 1 mole of substance, 1 mole of gas at constant volume. And if the temperature changes by delta T, when we are applying the heat, obviously the temperature will be changes. So delta T be the temperature changes. Then we can have Q is equal to mu CV delta T. This is a formula. Heat supplied to a system is equal to, that is proportional to CV dt or mu CV dt, where mu is the mole of the gas, amount of mole of gas. CV is the specific capacity, molar specific capacity at constant volume. Delta T is the temperature changes. Now, according to first law of thermodynamics, if you are writing the relation for Q, according to first law of thermodynamics, what is that? Q is equal to U, that is delta U plus W. Q is equal to delta U plus W, or else we can say delta U is equal to Q minus W. So here we can consider this expression Q is equal to delta U plus W. So here the constant volume process in the sense we can have change in volume is equal to 0, and also the work done will be is equal to 0. So what will be the formula? Q becomes changed into delta U plus 0 or delta U minus 0. Understand? So Q is equal to delta U. If we compare this Q and this Q, that means we can equate the right hand side. Delta U is equal to mu CV delta T. Delta U is equal to mu CV delta T, or else from this relation we can write CV is equal to 1 by mu into delta U by delta T. 1 by mu in delta U by delta T. Understand? If you are writing the limit delta T turns to 0, limit delta T turns to 0, we can write CV is equal to 1 by mu into du by dt. Okay. So since the temperature and internal energy are the state variables, this relation will be holds for any process. Okay. So we have seen some relation, that is when a heat is supplied to a system or supplied to the 1 mole of gas, the temperature becomes changes. So accordingly we can write Q is equal to mu CV delta T. According to first law of thermodynamics, we can have the formula delta U is equal to Q minus W, or Q is equal to delta U plus W. So since there is a volume process, constant volume process, dV is equal to 0, so work done will be equal to 0. So we can write Q is equal to delta U. So if you are substituting there this Q in this equation, or we are comparing these two equations, we can write delta U is equal to mu CV delta T, or else CV is equal to 1 by U into mu into delta U by delta T. And if the limit turns to delta T 0, we can write CV is equal to 1 by mu into du by dt. Now let's move on to an important question. Meyer's relation. Actually the Meyer's relation is Cp minus Cv is equal to R. Cp minus Cv is equal to R. This we are going to prove. Okay. Cp minus Cv is equal to R. Now let's consider ideal gas. Mu mole of ideal gas. Okay. Consider an ideal gas. The amount is mu mole. Mu mole of ideal gas, which is taken in a container with a volume V and pressure P, temperature T. Okay. Now, when the gas is heated at constant volume, gas is heated at constant volume, what will happen? The temperature will be increases by dT. So, temperature will be increases by dt. Temperature will be increases by dt. So that the internal energy may changes. Isn't it? If the temperature gets increases, the internal energy may changes. Actually, here no work is done on the gas, no, done by the gas. Okay? No work is done by the gas. So the heat that flows into the system will be increasing the internal energy. So the change in internal energy be change in internal energy be taken as du. Now let's find out the relation. So what is CV? CV is the molar specific heat capacity at constant volume. Then what is the value of du? Already we have learned the formula in the previous topic, that is CV is equal to what? 1 by mu into du by dt, isn't it? So from this we can write du is equal to what? Du is equal to mu into CV into dt. Let's consider this as equation 1. Okay. Now suppose the gas is heated at constant pressure. Here actually the gas is heated at constant volume. And now suppose the gas is heated at constant pressure. So temperature again increases by dt. Isn't it? What will be happening? Temperature increases by dt. Temperature increases by dt. So here Q be the heat supplied in this process, and the change in volume we can consider as dV. Okay. The volume change is considered as dV. Change in volume. For this we can write the formula for Q, heat supplied to the system. This also previously we have done. Q is equal to mu into, instead of CV here Cp dt. Mu into Cp dt. So this is equation number 2. Clear? So listen, we have taken a ideal gas, mu mole of ideal gas with the pressure P, volume V and temperature T. Now we are going to find the relationship of Meyer, Cp minus Cv equal to R. For that, first the gas is heated at constant volume. So the temperature is increases and it increases the internal energy. Change in internal energy occurs. So we can write the expression for molar specific heat capacity Cv is equal to 1 by mu du by dt, or else du is equal to mu Cv dt, where du is the change in internal energy and dt is the temperature changes. Similarly, when the gas is heated at constant pressure, so temperature again increases by dt. If the Q is the amount of heat supplied to the process, then the volume also will change. It will do dV. So we can write Q is equal to mu Cp dt. Okay. Now let's find the work done by the gas in that process. Work done. Work done by the gas. That is W is equal to P into V. Here we have considered the volume changed, but the pressure becomes constant. So we can write P into dV. Work done by the gas in this process can be as work done is equal to pressure into volume. So at constant pressure, the volume changes. So we can write W is equal to P dV. And from the first law of thermodynamics, we can have the relationship Q is equal to du plus W. Let's consider this as equation 3 and this as equation 4. Now let's substitute all the values. Q value, what is Q value? Mu Cp dt. Du value, what is du value? Mu Cv dt. W is equal to P dV. So substitute these 1, 2, 3 in equation 4. Substitute 1, 2, 3 in equation 4. So we can write mu Cp dt is equal to, what is du? Mu Cv dt plus P dV. Okay. Consider this as equation 5. Now we know the ideal gas equation. For ideal gas, the equation is given by, for ideal gas, the equation of state is given by PV is equal to mu RT. PV is equal to mu RT. So when we are differentiating this equation with respect to, that is differentiating on both sides, the differentiation actually done by means of UV method. That is, when we are differentiating two variables, first you make one variable as constant u and differentiation of second variable, plus next the other one will make us constant and differentiation of first variable. So this is the format we have to do the differentiation. So here also we can do the same. PV means when we are differentiating, we can have P into dV. P constant, V differentiate, plus V constant and P differentiated. So V into dP is equal to, here mu R or constant. So we can write a constant mu R into differentiation of T is dt. And if you are taking T as constant and if you are differentiating this one will be equal to 0. That is, constant differentiation is equal to 0. So PV equal to mu RT. When we are differentiating, we will be getting P dV plus V dP is equal to mu R dt. Here also, at constant pressure, we can have dP is equal to 0. At constant pressure, dP is equal to 0. So what will be the previous equation? That is P dV plus 0, dP is 0 is equal to mu R dt. P dV is equal to mu R dt. So consider this as equation 6. Okay. Now substitute the value of 6 in equation 5. Substitute the value of 6 in equation 5. So what is equation 5? Mu Cp dt is equal to mu Cv dt plus P dV. So we can write mu Cp dt is equal to mu Cv dt plus, instead of P dV, mu R dt. So everywhere the mole is there, mu can be cancelled. So we can write Cp dt is equal to Cv dt plus R dt. Again dt is common on both sides, so we can cancel dt we will be getting Cp is equal to Cv plus R, or else Cp minus Cv is equal to Cp minus Cv is equal to R. This is known as Meyer's relation. Understand? So listen. First we have taken at constant volume du, the internal energy changes is taken as du is equal to mu Cv dt. And at constant pressure Q is equal to mu Cp dt. So work is done by the gas. So we can have W is equal to P dV. According to first law of thermodynamics, Q is equal to du plus W. So substitute the du Q value and W value in this equation. Substitute 1, 2, 3 in equation 4. Mu Cp dt is equal to mu Cv dt plus P dV. Now we are going to substitute the value of P dV. For that we are taking the equation for ideal gas. The equation of state is PV is equal to mu RT. When we are differentiating this equation, according to UV method, differentiation of UV is U kept constant, differentiation of V plus V kept constant, differentiation of U. In that method we can write P into dV plus V into dP is equal to mu R into dt. Mu and R are constant. At constant pressure dP is equal to 0. Change in pressure is equal to 0. So this equation changed into PdV is equal to mu R dt. Now substitute the sixth equation in equation 5. We will be getting mu Cp dt is equal to mu Cv dt plus mu R dt, and mu and dt get cancelled. Cp is equal to Cv plus R, or Cp minus Cv is equal to R. So from this we can understand, for an ideal gas, the specific heat capacity at constant pressure is greater than specific heat capacity at constant volume. Okay, the molar specific heat capacity at constant pressure is greater than the specific heat capacity, the molar specific heat capacity at constant volume. Okay, because Cp is equal to Cv plus R. Understand? So from this we can consider specific heat capacity Sp, that is Sp is always greater than Sv. Understand? This is about Meyer's relation. Okay students, today we have discussed about specific heat capacities Sp and Sv, then specific molar specific heat capacity Cp and Cv. Then we have discussed some expressions, that is Q, Cp value and Cu value. Then we have found out the relationship of Cp and Cv. That is, you have to learn this question, very important question, derive Meyer's relation for an ideal gas. Derive Meyer's relation for an ideal gas. Study well, students. Thank you.